Let's start today's lesson by recalling the definition of a symmetric matrix. A square matrix A is symmetric if and only if A is equal to its transpose. Now remember, to do the transpose, we interchange the columns and the rows. So if once we exchange columns and rows, A is the same as the transpose, then the matrix is symmetric. Now another way of thinking about it being symmetric is the same on both sides of the diagonal. Now for symmetric matrices, we have this very important theorem, the real spectral theorem. If A is an n by n symmetric matrix, then the following properties are true. Now notice that these properties are only true for symmetric matrices. The first, A is diagonalizable. Now remember, in the last lesson we talked about what you have to do to diagonalize a matrix. Well, if it's symmetric, I know that it can be diagonalized. The second property that's true for symmetric matrices, all eigenvalues of A are real. And the third property, if lambda is an eigenvalue of multiplicity k, then lambda has k linearly independent eigenvectors. So we've already talked about the case that sometimes if we have a repeated eigenvalue, I can find multiple eigenvectors with it. They're linearly independent. Other times I cannot. Well, if I have a symmetric matrix, then I know that I can find the independent eigenvectors to go with a repeated eigenvalue. Look at an example. Find the eigenvalues and the dimension of the corresponding eigenspaces for the matrix 2, 1, 1, 1, 2, 1, 1, 1, 2. So I'm going to derive, and I'm going to author matrix A. I authored I, and then I did lambda I minus A. So here we have the matrix lambda I minus A. Then I authored the determinant of number 4 equal to 0 and told derive to simplify. So derive gave me lambda cubed minus 6 lambda squared plus 9 lambda minus 4 is equal to 0. Then I told derive to solve number 5 with variable lambda, and I got the two values of lambda. Lambda is 1 and lambda is 4. Now since A was a 3 by 3 matrix, I know that there is another, and with only two eigenvalues, I know that one of them is repeated. So I need to find out which one it is. So I have derive to graph lambda cubed minus 6 lambda squared plus 9 lambda minus 4. And I can see that 4 is a distinct root, but 1 is a root of multiplicity 2. So let's go back to the problem. It said find the eigenvalues and the dimensions of the corresponding eigenspaces. Well, lambda is equal to 4 is an eigenvalue. The dimension of its eigenspace is 1 because 4 was a unique root. It only occurred one time. This root of multiplicity was 1. We also got that lambda equal to 1 was an eigenvalue, and due to the real spectral theorem, I know that the dimension of its eigenspace is 2. If lambda is an eigenvalue of multiplicity k, then lambda has k linearly independent eigenvectors. So in this case, lambda is an eigenvalue of multiplicity 2. Then lambda has 2 linearly independent eigenvectors. If lambda has 2 linearly independent eigenvectors, then the dimension of its eigenspace is 2. A square matrix P is called orthogonal if it is invertible and P inverse is equal to the transpose of P. Now, of course, if it's not invertible, then we can't even talk about P inverse. So if we talk about if the P inverse is the same as the transpose of P, then the matrix is orthogonal. Look in the example. Determine whether 4, -1, -4, -1, 0, -17, 1, 4, -1 is orthogonal. Well, the first thing I want to do is to find out if it is invertible. Well, it's invertible if the determinant is not 0. Remember, if the determinant is 0, then it's singular. If the determinant is not 0, then it's non-singular, which means that it would be invertible. So I went to derive, and I had derive author the matrix, and then I told derive to evaluate the determinant. The determinant was 306, so that told me it was invertible. So I can invert it. Now I know it's invertible. The next condition that had to be true is that P inverse has to equal to the transpose. Now I had a couple ways of doing this. One way is I could calculate the inverse and see if they were equal. But if P inverse is the transpose, then that would mean that P times P transpose would have to equal to the identity. Because we know that P times P inverse is the identity. So if P inverse is P transpose and P times P inverse is the identity, then P times P transpose must be the identity. So I just had derive to calculate P times P transpose. I didn't get the identity. So since I didn't get the identity, that tells me that it is not orthogonal. Couple notes. Just you might need to use these in some of your homework assignment. An n by n matrix is orthogonal if and only if its column vectors form an orthonormal set. Now we've already talked about orthonormal sets previously, so you may want to go back and look up the definition of orthonormal set. But really what it means is all the vectors within all the columns be normal to each other, would be orthogonal to each other, and each of the columns would be unit vector. So orthonormal means that the vectors are mutually orthogonal, also that they're all of unit length. So those are the two things to be orthonormal. So the n by n matrix is orthogonal if its column vectors form an orthonormal set. So you take the column vectors, the n column vectors, all of the n column vectors would be mutually orthogonal and of unit length. If A is a symmetric matrix, n by n symmetric matrix, or let A be an n by n symmetric matrix, if lambda 1 and lambda 2 are distinct eigenvalues of A, then their corresponding eigenvectors are orthogonal. So if I have distinct eigenvalues, then the eigenvectors formed from those eigenvalues are orthogonal. Now, of course, I can make them orthonormal by simply finding the unit vector having the same direction. So I would just need to make the vector into the unit one by dividing by the length. A is orthogonally diagonalizable if there exists an orthogonal matrix P such that P inverse AP equal D is diagonal. So this is the same definition that we had previously for a diagonal matrix. If we can find an orthogonal matrix P, then it would be orthogonally diagonalizable. Well, here's where the square matrix comes in again. Square symmetric. A square symmetric matrix A is orthogonally diagonalizable and has real eigenvalues if and only if A is symmetric. So this is something special about symmetric matrices. If A is symmetric, then we know that it is orthogonally diagonalizable. And it will also have real eigenvalues. Now, we talked about this part before. And notice it is if and only if. So this theorem tells me that it can be done. If I have a square matrix, then I can orthogonally diagonalize it. The next frame tells me how to do it. The first step is to find all eigenvalues of matrix A and determine the multiplicity of each. Second step, for each eigenvalue of multiplicity 1, choose a unit eigenvector. Now, of course, to choose a unit eigenvector, you simply pick any eigenvector and make its length 1. And the way you do that is to divide the eigenvector by its length. For eigenvalues of multiplicity greater than or equal to 2, you find a set of k linearly independent eigenvectors and apply the Schmidt orthonormalization process. So for eigenvalues of multiplicity k, for k greater than or equal to 2, we find a set of k linearly independent eigenvectors, just like we've been doing, and then we apply the Gram-Schmidt orthonormalization process. Now, if you've forgotten the Gram-Schmidt process, go back and listen to the tape that goes through it, or hang on and I'll review you as I do an example in a few minutes. Step 4, we use the eigenvectors from steps 2 and 3 to form the columns of P. Then P inverse A P, which is equal to P transpose AP, will equal to D, will be diagonal. Now, P inverse is equal to P transpose in this case, because what we're doing is creating that orthogonal matrix P. So this was the definition of orthogonal matrix that we discussed earlier. Let's find an orthogonal matrix P that diagonalizes 0, 1, 1, 1, 0, 1, 1, 1, 0. Step 1 is to get the eigenvalues. Well, to get the eigenvalues, I want to examine the characteristic equation, which will be a determinant of lambda I minus A is equal to 0. So I have lambda times I minus A and I take the determinant of that and say it would equal to 0. So this would give us characteristic equation. Well, I think we can go ahead and do some of this in our heads here. That would be lambda minus 0, which is lambda. That'd be 0 minus 1, which is negative 1. 0 minus 1, which is negative 1. 0 minus 1, which is negative 1. Lambda minus 0, which is lambda. 0 minus 1, which is negative 1. 0 minus 1, which is negative 1. 0 minus 1, which is negative 1. Lambda minus 0, which is lambda, is equal to 0. Now, one way of doing this determinant, and the way we've been doing it, is use derive. But I decided, since we're nearing the end of the course, I'd go back and give you a little bit of review on the basic stuff, since the exam's coming up and so forth. So the way I could do the determinant would be to say lambda, negative 1, negative 1, negative 1, lambda, negative 1, negative 1, negative 1, lambda, and recopy the first two columns. Lambda, negative 1, negative 1, negative 1, lambda, negative 1. Now, as we come down this way, that's going to give me lambda cubed. Negative 1 times negative 1 times negative 1 is going to be negative 1. And this is going to be negative 1. Going back the other way, that's going to be positive lambda, but I had to reverse the sign, so that'd be a negative lambda. This would be a positive lambda, but I have to reverse the sign, so it would be a negative lambda. That would be a positive lambda, but going up reverses the sign, that would be a negative lambda. So I'd get lambda cubed minus 3 lambda minus 2 for my determinant. So going back, we have lambda cubed minus 3 lambda minus 2 equals to 0 is the characteristic equation. Now we need to solve that. Of course, if I tell derive to solve it, derive will be glad to do so, but we really know how to solve it if we have rational roots, especially. If we have rational roots, it would be plus or minus 2, plus or minus 1. And I can use synthetic division to find out which of these would be the rational roots, which if any. So let's try positive 2. And I divide the 2, and using the synthetic division, which works with only the coefficients, I've got the coefficient of lambda cubed is 1. There is no lambda squared, so its coefficient is 0. The coefficient of lambda is negative 3. The constant is negative 2. Bring down the 1. 2 times 1 is 2. 0 plus 2 is 2. 2 times 2 is 4. Negative 3 plus 4 is 1. 0 remainder. So that means I have factored this into lambda minus 2, because if 2 is a root, then lambda minus 2 is a factor, times lambda squared plus 2 lambda plus 1. Now, of course, the next term is mighty easy to factor. It's going to be lambda minus 2, lambda plus 1, lambda plus 1 is equal to 0. So we get lambda is equal to 2, lambda is equal to negative 1. And negative 1 is a root of multiplicity 2. Step 2, get a unit eigenvector corresponding to lambda is equal to 2. Now there'll just be 1 because lambda equal 2 was distinct. Well, for going back, now this is the determinant of lambda I minus A, but it would also be the matrix if I just take this much of it. So if lambda is 2, that means I'm going to have 2, negative 1, negative 1, negative 1, 2, negative 1, negative 1, negative 1, 2, times x, y, z is equal to 0. So I have 2x minus y minus z is equal to 0. A negative x plus 2y minus z is equal to 0. A negative x minus y plus 2z is equal to 0. Well, we can say that all these are going to have to be equal for that to work. So I'll let the x associated with 2 be the eigenvector 1, 1, 1. Now let's verify that 1, 1, 1 works. 2 times 1 is 2, minus 1 is 1, minus 1 is 0. A negative 1 plus 2 is 1, minus 1 is 0. A negative 1 minus 1 is negative 2, plus 2 is 0. So 1, 1, 1 is indeed the vector. But that's not a unit vector. So I had to take the 1, 1, 1, divide by its length. The length would be the square root of 1 squared plus 1 squared plus 1 squared. So that would be 1, 1, 1 divided by the square root of 3. Or I get the unit eigenvector of 1 over the square root of 3, 1 over the square root of 3, 1 over the square root of 3. Step 3, get 2 linearly independent vectors corresponding to lambda is equal to negative 1, and apply Schmidt. Well, if we go back, if lambda is negative 1, then you can see that's just going to give me all negative 1s here. This was the lambda I minus A. So in lambda I minus A, if lambda is negative 1, the net matrix would all be negative 1s. So I'd have the matrix negative 1, 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 negative 1. Now remember, this is lambda I minus A times x is equal to 0 is what I'm solving. So the eigenvector would be x, y, z equal to 0. Well, I'm going to get a negative x minus y minus z equals 0 all 3 times. So I need to create two solutions from this one. Well, first we'll let x equal to 0. If I let x equal 0, then y could be 1 and z could be -1. So I get 1x associated with -1 is going to be 0, 1, -1. We can get another x associated with it if we let y equal 0. Well, if y is 0 and x is 1, then z would have to be -1. So I get 1, 0, -1. So it would be a -1 minus 0, subtract a -1, be a -1 plus 1, which is 0. So here are two independent eigenvectors associated with the eigenvalue -1. Now they're not orthogonal right now, so that's why we have to apply Schmidt. Well, I'll review you on Schmidt. We need to find all W1 and W2 that are orthogonal. Well, the first thing was just let W1 equal to vector 1, which will equal to 0, 1, -1. And notice I'm just interchanging column vectors with n-tuples, because by now you know it means the same. W2 was equal to V2 minus V2 dot W1 over W1 dot W1 times W1. Now this is what Schmidt told me, the way of getting my second vector. So W2 is going to equal to V2, which is 1, 0, -1, minus V2, 1, 0, -1, times W1, dot W1, that's the dot product, 0, 1, -1, over W1 dot W1, 1, 0, -1, dot 1, 0, -1, times W1, which is, I'm supposed to be putting W1 under here, so that's going to be 0, 1, -1 times 0, 1, -1. Again, it is V2, 1, 0, -1, minus V2 dot W1 over W1 dot W1 times W1. So it's going to equal to 1, 0, -1 minus, okay, the dot product here, 1 times 0, 0, 0 times 1, 0, -1 times -1 is +1, over 0, 1, 1, 1 plus 1 is 2, times 0, 1, -1. Well, this is going to be 1 minus 0 is 1. 0 minus 1/2 is a -1/2. And that's a -1. Subtract a -1/2, which is -1 plus 1/2, which is a negative 1/2. So this tells me that W1 which is 0, 1, negative 1, and W2, 1, negative 1/2, negative 1/2, are orthogonal. Well, you can easily check that. That means their dot product would be 0. This is 0. That's a negative 1/2. That's plus 1/2. So it's obviously true. They would add to 0. So that proves they are orthogonal. But we needed to go one more step. They also need to be unit vectors. So I would take 0, 1, negative 1, divide by its length, which is going to be 0 squared plus 1 squared plus a negative 1 squared. So that's going to give me 0, 1 over the square root of 2, negative 1 over the square root of 2. Now I'll take the 1, the negative 1/2, the negative 1/2, divide by the square root of its length, which would be 1 squared plus a negative 1/2 squared plus a negative 1/2 squared, which is 1, negative 1/2, negative 1/2, divided by 1/4 plus 1/4 is 1/2, so that would be 1 1/2, which is 3/2. That would be square root of 3/2, which is going to be the square root of 6 over 2. I'll just say that. So this is going to be 1, negative 1/2, negative 1/2, divided by the square root of 6 over 2. Or if I invert and multiply, that's going to give me 2 over the square root of 6, a negative 1 over the square root of 6, because the 2's cancel, negative 1 over the square root of 6. Step 4 is to get P. So P would be the 3 eigenvectors that we have. Okay, go back and see if I can find the first one. I probably can't. So we have the first one here. That is the unit eigenvector associated with eigenvalue 2. So that would be the first column of P, which is 1 over the square root of 3, 1 over the square root of 3, 1 over the square root of 3. And now the second column would be the one we created from the 0, 1, negative 1, making it unit length. So it would be 0, 1 over the square root of 2, a negative 1 over the square root of 2. And the third column will be this column made into a unit vector, which would be 2 over the square root of 6, a negative 1 over the square root of 6, negative 1 over the square root of 6. So there is P. And that's what we were supposed to do. Find an orthogonal matrix P that diagonalizes the given matrix. So we have done that, and we have found P. Well, the next step, let's give the diagonal matrix D. Well, we know that D is equal to P inverse AP. Even though I did a lot of work by hand through there to kind of review you, I'm not interested in doing the inverse by hand. Of course, I don't have to. This would also be P transpose AP. But I'm not even interested in doing all that multiplication with the square roots. I could do it. It wouldn't be that bigger deal, but we're about out of time. So I did call in derive to do this one. And I went and I authored P. You'll identify this as being the matrix P. Now I told derive to do P inverse times A times P, and derive gave me the diagonal matrix.